Hi everyone, in this video we will learn about line integrals. So we have vector functions now, or vector fields as we're calling them, and you've learned how to do derivatives with, with them in previous class, which is Calc 3. And now the next section of this course, the next half of this course, is going to be about taking integrals of vector kind of functions. And the first type of integral that we will learn about is called a line integral, which is integrating over a curve rather than over an interval. So what does that mean? So far, our integration has been the following. Here's a function, here's an interval AB that's on the axis, and we divide this integral into infinitely many small parts, and we look at the corresponding parts and do our integration, which gives us the area or gives us the arc length or whatever. But we were so far working with intervals. However, now that we are in the vector world, we want to be able to work not just with the interval but with any curve. So the idea of a line integral is to be able to integrate on any curve, because now remember, because you're in the vector world, there's like arrows associated at each of these points, which means we're not adding up scalar values when we are doing integration anymore. We're adding up arrows, and these arrows can be oriented along any given curve. It doesn't have to be a straight line, it doesn't have to be an interval, but we can break it down in the same manner by choosing a bunch of points, which of course we will let go to infinity, and the basic idea remains the same. That is, for any interval we're going to pick one sample point. On that sample point we will evaluate what the function value is, and then depending on what it is that we are trying to evaluate, we will add those things up. And these curves are usually given in the form of parameters. So these are parametric curves given by x equals x of t and y equals y of t between some values a and b. So this t here is on an interval a to b, but the curve corresponding to the interval ab of time t could be any shape. Right, so these would correspond to the interval of time here. Right, so like t3, t4, etc. And that's between a and b. And then on the curve, we will take a bunch of these points which are infinitely close to each other or infinitesimally small, and then we will add whatever we are adding in order to find the line integral. So the difference, our regular integral is also a line integral, with the special case of the line being the x-axis, an interval of the x-axis. So the definition is the following. If f is defined as a smooth curve C, then the line integral of f along C is given by this integral parametrized, and we have this additional factor, which is your arc length factor. So this you will recognize is actually the arc length, right? So let's look at an example. Evaluate this line integral 2 plus x squared y ds, where c is the upper half of the unit circle, x squared plus y squared equals 1. So we have this region which is x squared plus y squared equals 1. Whenever we have a circle, the easiest parameterization we can use is cosine t and y equals sine t, so that this 2 plus x squared y ds then becomes 0 to pi, because it's only half a circle, 2 plus cosine squared t sine t, and the square root of dx over dt is negative sine t, and dy over dt is cosine t, which becomes sine squared t plus cosine squared t dt, which is 1. So this is simply 2 plus cosine squared t sine t dt. 0 to pi. If you take the integral, this is a 2t, and this one becomes, using u substitution, cosine cube t over 3, 0 to pi, 0 to pi. So you get 2 pi minus 2/3. Oh, two negatives become a positive, so you get a plus 2/3. So that's basically the line integral. So what is really happening is, you can think of moving along this curve and some sort of a density function that is given by 2 plus x squared y. So this, you can think of it as a wire that has some non-uniform thickness or density, and we are kind of adding them together to get the mass. That would be like a specific example of a line integral, but that's not what a line integral is. A line integral is simply an integral that is taken over a curve instead of over an interval. Now, next question is, what if the curve is made up of a bunch of different curves? And that's fine. Piecewise smooth curve, as long as things are all smooth, then if C is a union of all of these curves, then you can just consider it to be the addition of all of these curves. Meaning you can have a curve C, consisting of two different kind of shapes, which can have two different type of parametrization, and we can still work with it, because as long as everything is smooth, you can just add the line integral values. For example, evaluate the line integral 2x ds, where C consists of the arc of the parabola y equals x squared from 0, 0 to 1, 1. So 0, 0 to 1, 1, we have this shape, and then from here it's a vertical shape going to 1, 2. So it's a straight line. So I call this C1 and I call this C2. For C1, the parametrization I can use is x is x and y is x squared, so that over C1 I have 2x square root of dx over dx is 1, and dy over dx is 2x, 1 plus 4x squared dx, which, using u substitution, 1 plus 4x squared gives me du is 8x dx, or du over 4 is 2x dx. So this becomes, x goes from 0 to 1, 1/4 u to the 1/2 du, which becomes 1/4 u to the 3/2 and a 2/3, 0 to 1, which is just 1/6. Oh, sorry, the limits are going to change in u. Limits are going to be when u is 0, or when x is 0, u is 1. When x is 1, u is 5. So this is going to be 1/6, 5 square root 5 minus 1. And along C2, we have a simpler parametrization. X is 1 and y is y. So dx over dx is 0 in this case. And dy over is 1. So we have 2x dy from 1 to 2, but x is 1, so this is just 2 dy, which becomes 2 times 2 minus 1, which is 2. So the total line integral is 1/6, 5 root 5 minus 1 plus 2. Let's look at a problem where we can assign a physical interpretation to this. As I mentioned earlier, Mass when density varies along an object, right? The mass, in general, if you integrate the density function, you will get the mass. If you then do this, we get the center of mass, the x and the y value, which you've seen before. And the line integral can be thought of as an object that has varying density and a shape that's not a straight line, and we're trying to find its mass. So let's say a wire takes a semicircular shape of x squared plus y squared equals 1 and is thicker near the base than near the top. Find the center of mass of the wire if the linear density at any point is proportional to its distance from the line y equals 1. So let's draw a rough sketch of what's going on. We have a semicircular wire. It says that this is thicker near the base than near the top. So it's thicker at the base, which is at -1, 0 and 1, 0. And its density is proportional to how far it is from this line. So it's thinnest over here, which means that the further away from y equals 1, the thicker it is. How do we know that? We know that because we are told that it's thicker near the base than at the top. So it's thicker at the base and thins out at the top and thicker along the base again. Since the goal is to find the center of mass, first of all we got to find the mass. To find the mass, we need the density function. All we know is that the density function xy is proportional, so some constant, and 1 minus y. So this k is because of proportional. 1 minus because it's thicker at the base. Because if you do k times y, then it would be thicker closer to y, right? So we have k times 1 minus y. So when y equals 1, the density is almost 0, so it's the thinnest. And when y equals 0, which is at the base, the density is highest at the value of k. So the first thing we will find is the mass of the wire, which becomes the line integral of the density function along the curve C. But this is a semicircular case, so I have x equals cosine t and y equals sine t as parameterization, so that this now becomes k times 1 minus sine t dt, because the square root of, again, dx over dt squared plus dy over dt squared equals 1 for circular shapes. We've seen that. And this goes from 0 to pi. So this becomes k times pi minus a positive a cosine t, which will give you a 2. So you get the mass as k times pi over t. Now for center of mass, for x bar, it's 1 over m y times the density function, again the line integral. So it's going to be 1 over m y times ky, so y is now sine t times the density function, which is k times 1 minus sine t dt, going from 0 to pi. So that's 1 over m, or k over m, and an integral of 0 to pi sine t minus sine squared t dt. Integral of 0 to pi sine t dt is negative cosine t from 0 to pi, which becomes 1 minus negative, which becomes negative 1 minus 1, which is 2. And 0 to pi sine squared, we've seen this, we have to use half angle formula, and in this case the half angle formula would be 1/2 1 minus cosine 2t, and this will give me 0, so I'll just have a half from here. So I have k divided by mass, which is k times pi over 2. From sine t, we will have a 2 and a pi over here. And from here, we will have a pi over 2. So this becomes k times 4 minus pi over 2k times pi minus 2, and the k cancels out. So you actually get a numerical value for the x coordinate of the the y coordinate of the center of mass. And you can find the x coordinate as well, and it will come out to be 0, which will give you the center of mass as 0, 4 minus pi over 2 times pi minus 2. So that's one application of line integral. We'll end this video here. The next video we are going to go over line integrals which are with respect to x and y, and how to evaluate them. That's all for this video.